In this final part of Chapter 5, we'll cover dealing with uneven cash flow streams, various formats of rates of return, and loan amortizations. We saw in Part A what an uneven cash flow stream looks like with the values placed on a timeline. We can solve uneven cash flow streams in several ways, using the basic formula and solving more or less by hand, using the TI Business Analyst 2+, using the TVM keys, or using the cash flow worksheet, or using Excel. And we'll look at all of these. To find the present value of an uneven cash flow stream, you basically discount each cash flow appropriately and sum the discounted values. Note that the present value formula can be presented in two ways, with division and with multiplication involving a negative exponent. Taking the most fundamental approach, each cash flow is discounted back to time zero and summed. This can be done either using the formula, 300 divided by 1.04 raised to the third power, or using the TVM keys. Either of those methods are a bit cumbersome. Fortunately, the TI Business Analyst 2+ has a built-in worksheet to handle cash flow streams. To access it, press CF. Since the cash flow worksheet has a variable number of entries, it's very important that it be cleared before starting a new computation. To clear the cash flow worksheet, press CF, press second, clear work. The display will show CF0 followed by zeros. Remember that for a value to be entered in a worksheet register, it must be keyed in and you must press enter. Think of a worksheet like a column in Excel. To move to the next cell, you move down to the next register cell. In the TI Business Analyst 2, press the down arrow. The display will show CO1 for you to enter cash flow 1. Enter it, press enter, and press the down arrow again. The display will show FO1 for you to enter the frequency of cash flow 1. If successive cash flows are the same amount, you don't have to, but you can, enter each one separately. You can use the frequency counter to tell the calculator how many cash flows are the same in a row. The default value is 1. Continue entering cash flows and frequencies until all are entered. To find the NPV, press NPV. The display shows I is equal to 00, asking for the discount rate. Enter the rate as a whole number, press enter and down. The display will show NPV. Press compute and the computed net present value will be displayed. We're going to go through an example on the next slide, and there's a video tutorial that walks through the enter and down process. We'll be using this technique quite a bit, so it's important that you become comfortable with it. I strongly suggest you get your calculator and walk through this example step by step to be sure you're comfortable with the enter and down process. Start off, cash flow, second, clear work, clear it out. Cash flow 0, it's 0. Put a 0 and go down. Cash flow 1, 100, enter and down. Frequency is 1, you can just hit enter and down. Cash flows 2, 3, and 4, same process. Note that cash flow 4 is negative. You enter 50 and then the plus or minus key before you press enter. Press NPV, enter the discount rate of 4. Be sure you arrive at the correct answer. The TI Business Analyst 2 Cash Flow Worksheet video tutorial posted with this lesson walks through an example as well with a calculator simulator on screen so you can follow the keystrokes. This video covers using the Cash Flow Worksheet step by step. It also covers how to find the future value of an uneven cash flow stream, a function not provided in the TABA2+ student version. The tutorial is posted with this lesson, and I recommend you watch it and work through the examples with your own calculator to be sure you're comfortable with using the cash flow worksheet, because we're going to use it a lot in the coming lessons. Excel can also be used to solve for the present value of an uneven cash flow stream. One way would be to use the present value function individually for each cash flow and sum them up, much like using the TVM keys in the TI. Excel has a built-in NPV function that can be used as well. Note that the range in the Excel function begins with cash flow 1, not cash flow 0. We'll talk more about this in Chapter 11. For now, cash flow 0 in this stream is 0. Let's talk a bit more about interest rates, how they're quoted and used in time value of money calculations, and the impact of compounding period. The question here is, Will the future value of a lump sum be larger or smaller if compounded more often, holding the stated interest rate constant? This is meant to address the power of compounding. It's going to be larger. Look at the example. The more frequently interest is compounded, the higher the future value. Interest rates can be classified in three ways. The first and most commonly seen is the nominal or quoted rate. A nominal rate is by law quoted as an APR or APY. An APR is the periodic rate times the number of periods per year. The quote must contain a percentage and a period. For example, 4% compounded quarterly. Because of the way it's quoted, an APR can be converted to a periodic rate easily. 4% quarterly is 4% divided by 4 quarters equals 1% per quarter. The periodic rate is exactly what the name implies, the rate charged per period, and it's the one we use in calculations. As we saw, 4% compounded quarterly is 1% per quarter. 1% is the periodic rate. Remember our caveat about N, IY, and payment having to match in terms of period. Well, if the periodic rate is 1% per quarter, then N must equal the number of quarters, and if there's a payment, it must be quarterly. The third classification of rates is the effective annual rate. It converts a nominal or quoted rate to a rate that reflects annual compounding. With rare exception, an EAR is not used in calculation. Its main use is for comparisons. You're quoted one rate compounded monthly, another compounded daily. Convert both to EARs to compare them. A nominal rate can be converted to an EAR using the formula on the slide or using the Excel function. These effective rates demonstrate why it's important to convert APRs to effective rates for comparison. While the difference may be small, with large amounts of money, that small difference can make a big difference. APR and EAR can be equal, but only if the APR is an annual rate, M equals 1. If M is greater than 1, then the EAR is always greater than the APR. Nominal rates are quoted in contracts. They're not used in calculations or on timelines. Periodic rates are used in calculations and on timelines. Effective rates are used for comparisons. Matching periods is very important. The interest rate, payment, and time period must match. Annual periods, N equals years, IY is an annual rate, payment is an annual payment. Monthly periods, N is the number of months, IY rate per month, payment is a monthly payment. $50 per month is not $600 a year, nor is $600 a year the same as $50 per month. In both cases, the time when dollars are received affects the interest earned. This formula converts an APR or quoted rate to an effective rate. This formula converts an EAR to an APR. Fortunately, your calculator has a worksheet called the iConvert worksheet, which performs these calculations for you. The worksheet only has 3 entries: nominal, effective, compounding per year. You must enter the compounding periods per year. You can enter either nominal or effective and compute for the other. Excel has 2 functions which make these conversions as well, effect and nominal. Remember that in Excel, rates are entered as decimals. Can the effective rate ever be equal to the nominal rate? Yes, but only if the annual compounding is 1. Anytime the compounding period is greater than 1, the effective rate will always be greater than the nominal. For this problem, we have a 3-year annual $100 annuity with a rate of 4% compounded semi-annually. The $100 is paid annually, but the rate is compounded semi-annually. We cannot convert the $100 per year to $50 every 6 months to make the payment and rate match. One way to solve the problem would be to manually calculate each future value and add them up. Remember, we'll be using the semi-annual rate, 4% divided by 2, so it's 2% per 6-month period, and N is the number of 6-month periods. The first $100 is compounded forward 4 6-month periods. The second $100 goes forward 2 6-month periods. A second method uses the EAR of the rate as an annual rate. 4% compounded semi-annually equals 4.04% compounded annually. Now we can solve this as an ordinary future value of an annuity. Same answer. Solving for the present value of the same annuity can be approached using either method, discounting each cash flow individually and summing the result, or using the EAR as an annual rate and solving like a standard present value of an ordinary annuity, or use the Excel present value function. Loan amortization makes use of TVM calculations to find the payment that will amortize a loan to zero over a given period. The same principles apply to home and auto loans. Any loan designed to be repaid in equal periodic payments, reducing the principal to zero. Let's walk through a simple amortization example. We're borrowing $1,000 at a 4% annual rate to be repaid over 3 years. Step 1 is to find the equal annual payment. We're solving for an annuity payment. The loan amount is the present value, and it's positive since it's an inflow to you. Future value is 0 since the loan is to be paid completely to 0. N is 3 years, IY is 4. Solve for payment, which will be negative because it's going to be an outflow from you. Step 2, interest paid in the first year is the loan balance, $1,000, times the interest rate. 1,000 times 4%, $40. Step 3, the reduction in principal in year 1 equals the total payment minus interest. $360.35 minus $40, $320.35. To find the year 1 ending balance is the year 1 beginning balance minus the amount applied to principal. So that's $1,000 minus the $320.35, $679.65. The year 1 ending balance equals the year 2 beginning balance, and steps 2 through 4 are repeated. Loan amortizations are well suited to Excel, since once the first lines are set up, they can be copied down however many periods till the loan payoff. There's our payment, we calculated that. There's our interest. There's the amount applied to principal, the ending balance. The ending balance comes over to year 2, and we repeat. If done correctly, the ending balance in the final year will be 0. Note that with each payment, the amount of interest declines and the amount applied to the outstanding principal increases. As shown in the amortization table, over time, interest paid declines, the amount applied to the loan principal increases. This ends our coverage of the time value of money. As mentioned in the beginning of this chapter, time value of money is one of the most fundamental concepts in finance. We'll be using these techniques throughout the rest of the course, so take time to review as needed to be sure you're comfortable with making the calculations. I strongly recommend that you view the posted tutorials. In addition, the Excel examples used in this lesson are posted with the lesson for closer review.